some applications. So typical examples on page 985, example 7. This talks about temperature being written as a function of the xyz or xyz coordinates in the 3D space. And question says, in which direction does the temperature increase fastest at this point in space? So by our proof before, the direction in which the temperature increased the fastest is along the direction of the gradient. So we basically just calculate the partial derivatives being the xyz coordinates of a vector, right? And then you end up with this, and then now you plug in the values of xyz coordinates, and you get the gradient vector. And this is a vector being xyz coordinates, and this is a scalar here. And then in terms of a maximum rate of increase, we said the maximum rate, the increase is the maximum when we have cos theta equals to 1, right? So basically the maximum rate of increase is just the magnitude, the length of this vector. So then it's basically just the length of this vector. We're just calculating that. And that's just, x squared plus y squared plus z squared, all square root. And that's it. That's a very typical example. It doesn't get too much more complicated than this. And then I want to briefly talk about two things here. So when we have, at least in this textbook, we have two scenarios here. So basically either you have f of xy equals to z. So in this case, right, you have xy being independent variables, and then z being the response variable. And then we can have this, let's say, again, this goes back to my plane example here. So the gradient vector, basically the concept of a gradient vector is the gradient vector always is something that exists on the xy plane in this space, in this case. So basically the gradient vector only exists in the realm of the independent variables. The gradient vector only exists in the realm or space of the independent variables. So meaning in this case, the independent variables being x and y, the gradient vector is going to be a vector along the x, or rather a vector drawn in the xy plane or on the xy plane. Okay, it is not a vector in 3D space. That is not correct. And what is it perpendicular to? It's perpendicular to the level curves. Okay, so basically when we have z equals to f of x and y, the independent variable x and y form a plane, and within this plane we have gradient vectors and we have level lines, level curves, and the gradient vectors are perpendicular to the level curves. Okay, so I want to establish that because next I'm going to talk about one more variable here. So now here, this is harder to visualize because now we have basically we have another one. We have, let's say, we have a function called k equals to, now we have independent variables being x, y, and z, right? So then now there's just no physical way for me to draw the value of k because that's like 4D space, right? So here xyz, so now this 3D space, remember what I said, right? The gradient vector falls in the realm or space of independent variables. Independent variables in this case is x, y, and z. So this whole space, this whole 3D space is an independent variable, or are independent variables, right? So basically now you can see down here, this this is kind of like the attempt of the illustration here. So basically, now we're not talking about level curves anymore. Level curves, when we have this, when we have x of x and y equals to z, we have level curves. Now, when we expand it to x, y, z, then naturally we have level planes. So this would be like a level plane. Okay, so level plane meaning, along this plane of x, y, z values, the response variable value are all the same. And then so now the gradient vector. So obviously you have, you're gonna have gradient vector. You're gonna have fx, fy, fz. That's three components to a vector. So obviously that is a vector in 3D space, right? So in this case, the gradient vector is a vector in 3D space that is perpendicular to this plane. So that is just something I want to mention, because that's so that you don't get confused when the variable z is a response variable or independent variable, and you don't get confused when as opposed in terms of to what quantity is this gradient vector perpendicular to. Okay, so I want to reiterate that again. Let's look at this. So this one here, this is z equals to a function of x and y, right? So in this space, the response variable, basically you can draw it out in 3D space, right? It's a 3D shape, and the gradient vector is a vector in 2D space on the xy plane, and is perpendicular to the level curves. Okay, here when we have three independent variables x, y, z, the gradient, we're not talking about level curves. Now we're talking about level planes. Okay, so along that plane, the response variable values are all the same. And the gradient vector is a vector in 3D space, not 2D space, in 3D space perpendicular to the level plane. So that's just a distinction I want to mention.